Now let's look at some applications of this in types of questions. So if we're going to be given that e to the minus kx is the solution of this equation, so the second derivative minus 3 lots of the first derivative minus 4 lots of the original function is equal to 0. If that's going to be the case, can we find a value of k? Is there a valid value of k that would make that work? So where k is going to be a constant, k is going to be some constant number. So, well, let's start off. We get e to the power of minus k. That should be the power of minus kx. It hasn't been written properly. So that's going to be, if we get the first derivative, that would be minus k e to the minus kx up there. And then if we get the second derivative, because we're going to multiply minus by minus k, so it's going to be k squared e to the minus kx. So I don't know why it didn't come out nicely there. So there's our function, e to the minus kx, the first derivative, and our second derivative. Now what we want to do with that is take them and substitute them into this equation. So the second derivative was k squared equals e to the minus kx. Minus 3 lots of the first derivative, minus 3 times minus k e to the minus kx, minus 4 lots of y. So, and then that all is set equal to 0, because if this function is equal to 0, then that function is going to be equal to 0. So cleaning it up a bit, you're going to get positive 3k, because the minus times the minus, got the minus 4 there. What we look to do then is, like, we're looking for a value of k. So if we take e to the minus kx and factorize it out, because it's common to all of it, we get this function times this function. Now, if you consider e to the minus kx, that's going to be an exponential function. Now, if you remember your graphs of an exponential function, if we graph this one up, it would look something like that. Now, we know an exponential function would go through the y-axis, but it never touches the x-axis, which means that e to the minus kx is always going to be greater than 0. Because again, e is 2.718, so it's a positive number. Doesn't matter what it's to the power of, it will always be greater than 0. So we're going to ignore that part, because no matter what that is, that can't equal 0. So we couldn't have that being 0. The only thing that can be equal to 0 is what's in the bracket here. So if we set that equal to 0, is there values of k that we could find? Well, let's factorize it. We get k minus 1, k plus 4, because we've just done a quadratic factorization, which means that k minus 1 would equal 0, k would equal 1, or k plus 4 equal to 0 would give us minus 4. There's our values of k. But it relies on us realizing that part of the function can't ever be equal to 0. It just never will always be positive. So in question 5, we want to do some curve sketching. So we go back to our idea, turning points of the curve. How do we find those? We know that occurs when the first derivative is equal to 0. So we apply the product rule, so we derive x, and then have our second function, so x, so 1 times e to the 2x, and then we derive e to the 2x, which gives us 2e to the 2x, multiplied by the first function x, gives us that one there. So again, turning points occur when the first derivative is equal to 0. So we've got our first derivative equal to 0. E to the 2x outside of 1 plus 2x is our factorization. And again, e to the 2x can't be equal to 0. That's never going to be equal to 0. It's always going to be positive. So only the 1 plus 2x would be equal to 0, which means solving that only one turning point can exist when x is equal to minus a half. So when x is equal to minus a half, substitute it back into the original equation. So we get minus a half, e to the 2 times minus a half, so which would give us minus 1, or we could write it as minus 1 on 2e. So we want to find its nature, so if we test before the curve, before the point at minus 1, gives us a first derivative, that would be negative, so if we throw minus 1 in there, it gives us a negative value. If we put 0 in there, which is after minus a half, it would give us a positive value. So that means it's going to be a curve that's falling, 0, and then rising, which means it's going to give us a minimum value there. So that's what it's going to look like. That's our actual turning point. It's at a minimum. So what does it look like? Well, again, there's our turning point. It's a minimum. We know when x is equal to 0, y is equal to 0, because if we do the substitution in there, when x is equal to 0, y would be 0, so we know it goes through the origin. We know as x gets larger, the y values here will get really large, so that's why it starts to rise really quickly. And as it gets small, as x approaches negative infinity, well, that will get approach negative infinity, but that will get really small. That approaches 0. So seeing that's going to be negative, and that's approaching 0, that's why we get our curve that's below the x-axis, but going back up towards the x-axis, and y is equal to 0, because x e to the minus 2x. So if we consider when x approaches minus infinity, as we said, this part here, well, that'll approach minus infinity, but e to the minus 2x approaches 0. It gets really large. So it's really small. So that's why it approaches 0 there. Find the equation of the normals of the curve. Then, where the curve cuts the x-axis, well, we just said the curve cuts the x-axis at 0, 0. Get the equation of the normal requires us to find the equation of the tangent, the gradient of the tangent first. So again, when we sub in 0, gives us e to the 0, which is 1. That part would be 0, so it's 1. So that means the gradient of the normal is minus 1. So the equation of the normal will be y minus the 0, because we're using this value, this point, equals to minus 1 outside of x minus 0, which means x is equal to y is equal to minus x is the normal to the curve. Question 6, so again we want to play around with our first and second derivatives, applying the product rule. So find the first derivative, so 1 times e to the minus x, and plus x times the derivative of e to the minus x, which would be minus e to the x minus x, so you can see why it becomes negative. And then again we're going to derive that one separately, because that's not part of a product rule anymore. That's minus e to the minus x, and then derive e to the minus x there. So we get exactly the same as we did there. So that's why it's minus that one, and then plus that one. Collecting our terms, so minus 2 e to the minus x. So there's our first derivative and our second derivative. Be really careful that you see that I'm applying the product rule again on that part to give us that. And be really careful of the signs. So what we want is a set of values of the function where e to x times e to the minus x is decreasing and its graph is concave down. So if it's decreasing, that means our first derivative is less than 0. We've got to remember what these terms mean. Decreasing, the first derivative is less than 0. So we take our first derivative, make it less than 0 again. So again, when we consider this, e to the minus x, if we want this whole function to be less than 0, then that part there is always going to be positive, because it's 1 on e to the x. Remember, it's going to be a function that looks like that. So it's always positive. So that can never be negative, which means if this function here, e to the x times 1 minus x, is going to be negative, that means 1 minus x has to be negative there. So where is that going to be less than 0? It's going to be the case when x is greater than 1. So for the second derivative to be concave down, we know that's going to be less than 0 as well. So we do the same thing. We factorize our second derivative. E to the minus x is going to be positive. So only this part of the function can be less than 0, because where we want to see if that's the whole thing's going to be less than 0, that part's got to be less than 0. It's got to be a negative. So we solve for that and we get that x was going to be less than 2. So there's your region. Only when x is greater than 1 and x is less than 2 is the curve decreasing, but concave down as well. So between those two x values is that going to exist. Question 7, again finding stationary points, e to the x on x. So this time we're going to use quotient rule. So it's going to be e to the derivative of e to the x times the x minus derivative the top times the derivative of the bottom, which is 1, and that should be over x squared. This squared's been left out. Not that it really matters, because we know stationary points exist when the first derivative is equal to 0. So if that's the case, then only the top can be equal to 0. We can't divide by anything to make it equal to 0. So only the top can be equal to 0. So we set it equal to 0 again. E to the x is going to be factorized out. But again, that can't be 0. So we're going to ignore it. So that's where we get the x minus 1 equal to 0 or x is equal to 1. When x is equal to 1, y would be equal to e, so the 2.71. You could differentiate again. Not pretty to differentiate again whenever you started with a quotient rule. So I've preferred to prove that it's a minimum by testing the first derivative on either side of 1. So I've tested a half, put it in the first derivative, we get a negative value. Put in 2 into the first derivative, you get a positive value. So the curve is falling, 0, and then rising again. So it's a minimum turning point. So find the equation of the tangent to the curve here. E to the minus 2x, 2x minus 3, where x is equal to 1.5. So what do we need? We need the first derivative to give us the gradient formula function. So we derive 2x minus 3, that's 2 lots of e to the 2x minus 3. When x is equal to 1.5 as well, we get our gradient then being 2. When x is equal to 1.5, we sub that in, we're actually going to get y is equal to 1. Because that will give me e to the power of 0, which is y is equal to 1. So there's the point, 1.5, 1. Gradient of 2, sub them both in, or the point and the equation. We get the graph looking, we get our expansion looking like that, collect our like terms to give us our equation of our tangent. So all the applications we've done before can be done with exponential functions. So it's not a problem to do any of those. You've just got to, instead of using polynomials as we've done before, use the exponentials and be careful about making sure we derive our functions properly, whether it's straight out application or a product rule or a quotient rule.